All right. So first one. Electrostatic interactions. Electrostatic interactions. Simply put, what are electrostatic interactions? Yeah, just plus and minus. That's all it is, plus minus attractions. So most of the intermolecular forces we're going to talk about in the context of being inside an aqueous medium. Why are we going to talk about this being in water most of the time here? Well, biochemistry, and we're looking at inside the body, inside cells. It's an aqueous medium. So that's why we're going to look at most of these things in an aqueous medium. So in an aqueous medium, when you see plus and minus attractions going on, that's electrostatic interactions. So we also got hydrogen bonding. So this is one you learned back in Gen Chem. You would have seen it again in OChem, but you'd be surprised at how many students still don't quite have a grasp on what hydrogen bonding is. So, and being that this whole chapter is supposed to be about water, we're going to look at hydrogen bonding in the context of water. Cool, so hydrogen bonding. So I like to think of hydrogen bonding as just a super duper duper dipole force. So you guys learned about dipole forces back in the day. There are some handouts there, guys, by the way. So dipole forces, just partial positive with a partial negative. So, but for hydrogen bonding, I like to think of as super duper dipoles between partial positive and partial negatives. In this case, it is the lone pair on a very electronegative atom, and we'll talk about which atoms qualify, and the interaction between a very positively polarized hydrogen. So how do you get a very positively polarized hydrogen? So what's that? Dipole, but who's that hydrogen got to be bonded to then? Electronegative atom. In Gen Chem, you would have learned it was FH, OH, and NH, the phone elements. So you're going to get a little bit different here thing in biochem. One, we probably won't ever talk about FH. Why won't we ever talk about FH? Well, the only molecule that really has an FH bond is HF. And we're not going to put that in the body and talk about it in biochemistry. It'd be very terrible. So you're probably not going to see this guy too much in a biochemical context or even at all. So, but we'll add one more on here. So, and that's SH instead. So an SH, so we don't usually talk about this guy in a regular general chemistry class, but in biochemistry, cysteine residues have an SH bond, and it actually comes into some relevance. A little bit weaker than either the OH or the NH in terms of strength of the hydrogen bond. So, but it's a new one you should totally take into account. So you may not have counted these before. You're definitely going to want to count these now. Sweet. So here in this case, this hydrogen is definitely partially positive. It's the hydrogen bonded to an oxygen, so he qualifies. And it's his interaction with the lone pair of electrons on another sulfur, oxygen, or nitrogen. That's what we're looking at. So you may get some big molecules, like some of the amino acids and stuff like that, and you may just be asked to look for all the hydrogen bond donors and hydrogen bond acceptors. Now, it's a little bit different, so don't think of like Lewis acid-base type stuff. You're talking about hydrogen bond donors. Everything's defined a little bit differently. So in this case, the atom that has the lone pair in the interaction would be called the acceptor. The atom who has the hydrogen would be called the donor. So notice the donor is not really the hydrogen itself, but the atom who's got the hydrogen, in this case the oxygen up here on the top water molecule. And that's your donor and acceptor. And so you may get a big molecule, and just be asked how many different donor atoms and how many different acceptor atoms on there. And so for donor atoms, you're looking for any atom that has a hydrogen who's an oxygen, nitrogen, or sulfur. So any nitrogens, oxygens, or sulfurs that have a hydrogen, they're donor atoms. So, and then for acceptors, you're looking for any oxygen, nitrogen, or sulfur that has a lone pair, but it has to have a lone pair. It's the lone pair that makes it a good acceptor. But that's your hydrogen bonding. This is one of your stronger intermolecular forces, right, from back in the day. So one thing to note about water's hydrogen bonding. So why is this pretty darn important that water does hydrogen bonding? Come up with a variety of reasons for why it's important. Any? So be a liquid at room temperature. That's kind of important. Water's kind of this universal solvent and the biochemical solvent. And it's liquid at room temperature, one, and over a wide range of temperatures. And if it freezes or if it boils, that's not going to be a good solvent anymore. Has a great high boiling point. And same kind of thing, and high heats of vaporization, high heats of fusion. So it takes a lot of heat to melt ice. It takes a lot of heat to boil water, even when you're at the phase transition temperature. But again, it exists as a liquid over a wide range. If that wasn't true, so then again, being the universal solvent for life, we kind of have some issues over the range of temperatures at which life would really be possible. Cool, some other things, it's got really high surface tension as a result. All the water molecules on the surface so attract each other. So, and what allows us to walk on water, right? Well, by us, I mean if you're a water bug. If you're a water bug, that's what allows you to walk on water. So you and I, on the other hand, we're a little fat. And we're too fat to walk on water. We're a little heavy, and we just break these just by stepping in the water. But the water bug, on the other hand, being light and having a broad surface area, it can just walk on the water because of this interactions here resulting in a high surface tension. Cool, so all those lovely things about water. So and it turns out if this wasn't true about water, there's some other reasons so that you might investigate in some other classes, but life would probably in all likelihood not be possible without water. That's why when they look at Mars, and they're looking for the presence of water because they're like, oh, if there's water, maybe there's life. And kind of the converse is if there's no water, there's probably not life. So it's kind of what we think is pretty much one of the bare necessities for life. All right, next one on the docket, dipole-dipole forces. So dipole-dipole forces, it's just the interaction of the dipole of one molecule with the interaction of the dipole of another molecule. So what do we call molecules that have dipoles? Polar. So here's HCl, definitely a polar molecule. Chlorine's more electronegative than hydrogen. Sometimes we draw the dipole in like this, pointing towards the more electronegative of the two atoms in that molecule. So other times we might just show the partial charges. The more electronegative atom has the partial negative charge. The less electronegative atom, the partial positive charge. This is the Greek letter delta, meaning partial. And same thing on the other molecule here. So then between these two molecules, you might have a weak interaction. The partially negative chlorine is attracted to the partially positive hydrogen, and this weak interaction here is what we call a dipole-dipole force. Notice it's an intermolecular force here when it's between two molecules. But as we'll see a little bit later, we call it an intermolecular force, but in the context of like peptides and proteins, it's one giant molecule that might be interacting with itself. So would it really be proper in that context to call it an intermolecular force? What would it be called instead? Intramolecular force. So I've called these intermolecular forces, that's how they were introduced in Gen Chem, but we'll actually see these often interacting as intramolecular forces today, just because we're dealing with these big biomolecules. Cool. Dipole-dipole force, a little bit weaker typically, actually I say a little bit, significantly weaker than hydrogen bonding. Dipole-induced dipole. So dipole-induced dipole, a little bit different. This one doesn't get a lot of press. It's not something that's super important, but I put it on the list. It is definitely weaker than dipole-dipole. But it is the interaction of one molecule's dipole causing or inducing another molecule to have a dipole and therefore interact with it. So a molecule that has a dipole is what again? Polar. And what we do is we usually look at this interaction as being between a polar molecule and a nonpolar molecule. So in this case, who should we pick on? We'll pick on Keon over here. So let's say that I'm a polar molecule and Keon is nonpolar. Is there any reason Keon should like me? No, not at all. Except I come over here and I'm polar. And facing Keon, I'm a little bit negative. And so Keon, as a result, shifts his electrons around behind him. So that way facing me, he's a little bit positive. And he only does this in response to me. I've induced him to have a dipole. And now Keon's like, wow, Chad's pretty cute. Sweet. Thanks, Keon. I appreciate your opinion. So cool, that's a dipole-induced dipole. Usually we look at that again between a polar and a nonpolar molecule. So finally, we get to London dispersion forces. So this was the weakest of the intermolecular forces you looked at in a Gen Chem class. All molecules have these, and it's just an induced dipole. So let's take another example here. Let's pick on Keon again. He worked out well for that. So now I'm nonpolar and Keon's nonpolar. So it turns out all molecules have these, both polar and nonpolar, but they're most significant, they're most important usually to talk about when we talk about nonpolar molecules. For a nonpolar molecule, this is all they have. So now me and Keon are both nonpolar molecules. Is there any reason I should like Keon? Is there any reason Keon should like me? No, there's no attraction here whatsoever. It's like, I don't hate him, but I'm just like, okay, it's Keon. So, but my electron cloud might be swirling around me. Notice the electron clouds are not static, they're in motion, right? And so maybe at one point in time, my electron cloud is more in front of me than behind me. And so facing Keon, I'm a little bit negative right now. In a minute, it might change, but right now, I'm a little bit negative. So Keon, in response, swings his electrons around behind him. And so facing me, he's a little bit positive. Notice these are temporary or transient dipoles, inducing dipoles in other molecules. We sometimes call this induced dipole for these London forces. So, and all of a sudden now, I'm like, Keon, you look like a great guy. We should hang out sometime. And Keon's like, yeah. And then my electrons move around. I'm like, oh, never mind. So I don't know what I was thinking. So it is a weak, temporary, transient dipole interaction. So sometimes called an induced dipole interaction. So, but they're weak, but the bigger a molecule is, the bigger its electron cloud, the heavier it is, the bigger these appreciate. So notice, if I look at a small molecule like hydrogen gas, H2, its London forces don't amount to much at all. It's a really tiny molecule. However, if I look at a protein, even a very hydrophobic protein that's fairly nonpolar, proteins can get really large. And all of a sudden now, these London forces for such a large molecule can add up significantly. So it's dependent on size. All right, one last thing. This is not something you would have talked about in any other class in all likelihood. So these are your hydrophobic interactions. So hydrophobic interactions, we'll talk about these pretty much in the context of protein folding and almost nowhere else in all of chemistry. So, but really super important in protein folding. So hydrophobic interactions are only something you'll also talk about in an aqueous environment in water. So if you look, so if I go to put like say salt, NaCl in water, will it dissolve? Pinch of salt in water? Yeah, for sure. Why does it dissolve? What's that? I'm looking for a slightly different conceptual reason than that. So what is water? Polar or nonpolar? It's pretty darn polar. This level of hydrogen bonding makes it really polar, in fact. So, and being really polar, it likes other stuff that's really polar. And salt, rather than simply being really polar, is actually ionic, but it dissociates into ions, and those ions get, we say, solvated, surrounded by water molecules. If I am, say, a chloride ion, what charge do I have, first of all? Negative. Which part of the water molecules do I like, oxygen or hydrogen? Hydrogen. Hydrogens are partially positive. In fact, I'd get surrounded by water molecules, and they'd have their hydrogens facing me. So that's what I would interact with. That would actually be called an ion dipole interaction. So however, what if I'd been a sodium ion? If I'm a sodium ion, what charge do I have? Positive. And what part of water do I like? Oxygen. And now I'd get surrounded by water molecules with the oxygens facing me. So but because I'm charged, so I interact with water very well. And water dissolves, you know, being polar, other polar stuff very well, and ions typically as well. However, if we look at the converse, if I look at something very nonpolar, water don't like you. If you're nonpolar, water's got nothing to do with you. Water doesn't like you. So in fact, we've picked on Keon enough, we'll pick on Elizabeth. So let's say Elizabeth is a nonpolar molecule, and we're all water. And we're like, somebody doesn't belong, right there. She doesn't belong. So in fact, it gets worse than that. We just can't stand Elizabeth. We're like, oh gosh, look, elephant in the room. And what happens is the water, in isolating the rest of the water molecules from her, the water surrounds her in a highly ordered solvent cage is sometimes the word we use. And it's a highly ordered structure. Our highly ordered structure is usually a good thing to form spontaneously. Not so much. And so we don't really want her to be dissolved in us. And if she dissolves in us, that's what we got to do. We got to form this highly ordered structure, I like to think, to protect the rest of the water from her. So what happens instead is if there's a bunch of Elizabeths in the room, they all just kind of go hang out with each other. And the water just hangs out with the water, and they stay separate as much as possible. So the interaction of Elizabeth with all her other nonpolar friends together, it's not so much that they're all attracted to each other so much, it's just that they hate the water as well. So, and that's called the hydrophobic interaction. So, and it's really driven in large part by entropy considerations. So dissolving something nonpolar in water would take a lot of entropy, and therefore it's not favorable. And so all those nonpolar molecules interacting with each other instead, and to the exclusion of water, becomes very, very favorable. Cool. So this hydrophobic interaction, again, we'll use this to talk about protein folding, but this is why nonpolar residues in an aqueous environment tend to just coalesce all together. Really important in protein folding. Any questions on these? I said intermolecular forces, but again, as we'll see, a lot of intramolecular forces in today's lecture. Sweet.